Hello, my people. I hope we're doing well. We're moving on from inverse trig as a function to talking about it as an operation. Kind of like I said in class, I cut and pasted this from two different sheets in the previous document. This actually corresponds to that column, and that actually corresponds to that column, right? And the whole idea is that when we are given something that is like square root of 4, it is as if we are being asked, for f of x is equal to square root of x, what is f of 4? Okay, and that, because it's a function, has one output. Here, where we're actually solving what satisfies both of these, we're not sort of bound by those constraints. And the same thing with inverse trig. Okay, when I'm given the inverse trig function arctan of x, and I'm asked what is g of 1, I'm asking, because of the constraints that define a function, I'm being asked what is that one value. When I'm taking inverse trig and using it as an operation to solve a trigonometric equation, I am not bound by those constraints. So in the previous, yesterday and in the previous video, we focused on inverse trig as a function, sort of being given an inverse trigonometric expression. Today we'll be focusing on inverse trig as an operation, and let's go ahead and jump into some examples of that. Now, we have, let's say we're given sine x is equal to negative root 2 over 2. And basically it's saying, for what angle measurement does sine have a ratio of root 2 over 2? And if you think about it in terms of a negative root 2 over 2, if you think about it in terms of the graph, okay, hello, Mr. Y is equal to sine x equation. Where do you have an output of negative root 2 over 2? Well, we can go ahead and draw in negative root 2 over 2, which, by the way, is approximately negative 0.707. And you notice that it intersects the sine function at those regular intervals, okay? Because of the periodic nature of the function, those points of intersection happen every period. But notice that, the distance between these two is not the same as the distance between these two, right? So I need to actually find both of those. We can see the same sort of thing here on the unit circle, because when we're asked where is a sine ratio a particular value, you're thinking of, up and down along the vertical axis, along the y-axis, because remember, in our order pairs, they are cosine theta, sine theta. Sine theta is represented by our vertical displacement, because that's what it means to be right there in the y-coordinate. Alrighty, well, we go ahead, come down here, and again, draw ourselves a nice line at y is equal to negative 0.707, and basically draw it across to both points that would correspond to that y-coordinate. And if we do that, we can then, draw the ray, which defines the terminal side of that angle, and we get two answers, right? We get 5 pi over 4, and we get 7 pi over 4, okay? This is 5 pi over 4, and this is 7 pi over 4. Now, if we were being asked to provide the answer for this on the implied domain, it would not only be 5 pi over 4 and 7 pi over 4, it would be all of their coterminals. And equations like this sometimes come with specific instructions, and they say something like, evaluate on, 0 to 2 pi. And if they do that, then your answer is simply these two right here, because both of those exist on that interval. Now, if it basically doesn't give you those restrictions, or it says, evaluate on negative infinity to infinity, Then we have 5 pi over 4 and 7 pi over 4, but we need to somehow represent that it's not just those values, but every period, and in this case, every coterminal before and after that. Well, if you go around to 5 pi over 4, you can get to this terminal side again just by adding 2 pi, and then adding 2 pi, or subtracting 2 pi, and subtracting 2 pi. So what we do is we add 2 pi in, where n is understood to be every integer. And the same thing for 7 pi over 4, okay, where 2 pi n is basically understood to be the set of all integers. And so this is the way we represent 5 pi over 4 and every period before and after it. And this is the way we represent 7 pi over 4 and every period before and after that. You just have to be careful about what the instructions are and whether there's a specific interval of solutions that you're being asked for, or whether you're being asked for all of them. Okay? Alrighty, well, let's move on to cosine. Okay? And let's say that we're being asked what angle measurements give us a cosine ratio of 1/2. Well, we can go ahead and actually draw y is equal to 1/2 and see where it intersects the cosine graph. And we see the fact that it actually does so periodically, right? And so if we look at just, one period right there, we see the fact that, it looks like right just over 1, which of course would be pi over 3. And right over here, and because it's symmetric, you would expect that to be, pi over 3 shy of 2 pi, okay? But we see the fact that this has exactly the same shape and proportional to its period, exactly the same points of intersection. And so all we have to do is we need to basically find those 2 points. Well, we can do that, okay? And we can use the unit circle as well. We basically come here, and since cosine is on the unit circle represented by our x displacement, our horizontal axis, where instead of putting a horizontal line defined by a particular y value like I did for sine, I'm going to put a vertical line that represents a particular horizontal displacement of 1/2, right? And then I'm going to construct the rays that represent the angle measurements associated with the points where it intersects the unit circle. And that, of course, right there is pi over 3. This, of course, right here, you can call it negative pi over 3. That would be over here. Or, since, we're kind of thinking about 0 to 2 pi right now, basically that winds up being 5 pi over 3, because it's 6 pi over 3 minus pi over 3. And if you were asked to evaluate, on 0 to 2 pi, you would just give me x is equal to pi over 3 and 5 pi over 3. If you were asked to evaluate on negative infinity to infinity, you would give me pi over 3 plus 2 pi n and 5 pi over 3 plus 2 pi n. And we'll get to examples where the 2 pi n actually changes because you're dealing with a trigonometric equation where the period has changed. But for right now, we're just kind of doing the training wheels questions like this, where we have not seen a transformation of a change in period. We're simply dealing with cosine in and of itself. Okay? Alrighty. Okay. Well, for some odd reason, I forgot to put the actual value right here on this one. That I'm thinking yeah, that's root 3 over 3. That's root 3 over 3, okay? y is equal to root 3 over 3, which, by the way, just approximates to 0.577. And as we notice, it's just below 0.6 right here. So that kind of makes sense. Now, if we're looking for where tangent is equal to root 3 over 3, that's another way of saying where is it equal to 1 over root 3, right? Because root 3 over 3, we arrived at that value, and it's familiar to us because what we had really done is we had arrived at a sine ratio of 1/2 and a cosine ratio of root 3 over 2, or alternatively, a sine ratio of negative 1/2 and a cosine ratio of negative root 3 over 2, and we had simplified and then rationalized the denominator. So, when you look at tangent of x is equal to root 3 over 3, you might want to think about the fact that it really represents these relationships insofar as we are interested in unit circle values and using the unit circle, okay? But we notice that because of, again, the periodic nature of the tangent function, that these points intersect, and therefore revealing that tangent has an output of root 3 over 3 periodically, right? Once a period. So we simply need to find out where that first one is. And again, when we're dealing with the unit circle, it's so easy to deal with sine and cosine, but it still can be helpful for us when we're dealing with things like tangent. Now remember, like in the lecture video, I reminded you that right on this point at pi over 4 and 3 pi over 4, this is where tangent is equal to 1. Tangent is equal to 1 here, and tangent is equal to 1 here. Tangent is equal, so tangent of 0 is 0. Tangent of pi over 2 is basically undefined. But right here, tangent of pi over 4 is 1. So if you're looking for a ratio that is between 0 and 1, you're looking for tangent in here, okay? So in here, you're going to have a tangent, right, ratio between 0 and 1. Up here, and of course opposite over here, because the ratios are going to be identical, except they're going to be negative over a negative. And so you're really looking for you're looking for angle values in these two regions. Well, if I know that that is where sine is 1/2, okay, and cosine is root 3 over 2, it's right over here at that pi over 6 value. But pi over 6 is not the only angle measurement that has that tangent ratio, because the ordered pair right here, which is root 3 over 2 1/2, has its negative over here, negative root 3 over 2 negative 1/2. And that right there is pi over 6. But remember that the period of tangent is pi, and it has identical values exactly across the unit circle. Exactly across the unit circle is a fancy way of saying plus pi, okay? And so our answer here is x is equal to pi over 6, not plus 2 pi n, but plus pi n, if we're looking, on the implied domain. If we're looking on 0 to 2 pi, we would, of course, just include just these two values, just the pi over 6 and just the 7 pi over 6. So pi over 6 and 7 pi over 6, and there we go. It's a little more indirect when you're trying to mine the unit circle for tangent values, but after you sort of recognize the way that tangent values pop up in patterns on the unit circle, you can still sort of use it as a visual guide for those things. All right, let's go ahead and look at this one. Now, cosecant x is equal to negative 2. Now, most of you are going to automatically go, okay, that is simply asking where sine x is equal to -1/2. And, kudos to you. But I do want to show you that it actually does have a graphical representation on the original cosecant. There it is, okay? Now, if I were to actually, graph the sine function as it goes through here, that is implied to sort of be sandwiched in the midst of this, and then actually drew in the y is equal to -1/2, I would get exactly the same input values, right? So let's go ahead and let's just pop down here to the unit circle, knowing that sine x is equal to -1/2. Boom, right there, right? Because sine, remember, is measured along the y. And then I know that I have 2 points on the unit circle that correspond to that. This point here and this point here. And those have rays that create the terminal side of angles that are associated with those points of intersection. And so I have, this angle measurement and this angle measurement. This one over here is 7 pi over 6. This one over here is 11 pi over 6. Now, this right here, sort of over here, is 2 pi. Do these points look like they're 7 pi over 6 and 11 pi over 6? Yeah, they kind of do, right? Because pi would be right about here. And then basically this is just a smidge over pi, and this is just a smidge shy of 2 pi. And we do have that. Now remember, again, if we're given a particular interval, then we basically say, okay, well, it's 7 pi over 6 and it's 11 pi over 6. If you are not given, if you were basically given on the implied domain, then you need to account for the continued values that will give rise to a cosecant ratio of -2, and those of course are the coterminals. And you have x is equal to 7 pi over 6 plus 2 pi n and 11 pi over 6 plus 2 pi n, and that would be your answer. Alrighty. I'm going to go ahead and bring this video to a close since it's a nice stopping point, and we will deal with the non-unit circle ratios and start venturing into using inverse trig to identify significant points on a transformed trigonometric graph, as we did in class. Okay. As always, if you have any questions, please do shoot me an email or a chat. Bye.